Good morning, everyone. Okay, next, we want to look at mechanics of power screws. A power screw is used to change an angular motion into linear motion, simple definition. So, and this happens, of course, if you have a screw, if you rotate it, it would move. If you go like clockwise, it will be moving, in this case, will be moving downward. If you move counterclockwise, it will be moving outwards or upwards. It usually transmits power. Example would include vices, presses, jacks, lead screws on lathe. And here we are looking at an example of an Acme thread power screw jack. So again, as we rotate the nut, the screw is going to move in the vertical direction. Power screws typically would have either square or Acme thread. So a square thread looks exactly like a square, where we have here the pitch measured between the distance from one thread to the next, the distance from one thread to the next. And a square thread, of course, is difficult to cut, and you see it makes a right angle. And the Acme threads, we do have a lead angle of 29 degrees, so half a lead angle here would be 14.5. And again, we have the pitch and the height of the thread is P/2. The effective height here is half the pitch. This is also the same for a square thread. In table 8.3, we have preferred pitches for Acme thread. So for each diameter, it tells you what is a preferred pitch, depending on the measure or the nominal diameter of your rod. The idea or the mechanics of a power screw is similar to those of standard basic machines, where we have this helical shape at an angle. So basically, we're looking for the idea of mechanical advantage or the ease of lifting a load without exerting a force that is equivalent to that load, which remind us was the idea of a lever or using a wedge, where there is an inclined plane. You see here the threads are at an angle. The threads are at an angle. And this angle would be referred to as lambda. This inclined plane makes an angle lambda. And the force that I'm trying to lift would be the force F. So like we use a wedge, we're going to use this analogy. Now, of course, if I look at when I make one complete rotation, I am looking at going through the perimeter of my screw. So if I open this and use the median diameter, dm is the diameter, the average between the major and the minor. So the perimeter of this would be pi dm. So if you look at the distance I'm going to move would be pi dm. So if my load is exerting a downward force F, now when this is applied to an inclined plane, we are going to have a friction resistance. If I'm trying to lift this friction resistance will be acting in the opposite direction, which would be the downward direction. So what I'm trying here is I'm trying to apply a force through the torque to push this load upwards on the inclined plane to get this mechanical advantage. Now the friction resistance is equal to the coefficient of friction multiplied by the normal force or normal reaction from that inclined plane. So I have here Fn, I have here the raising force, which is P, pushing to try to move that load upwards along the inclined plane. So this would be to raise the load. If I am trying to lower the load, I am pushing in the opposite direction by this force PL, and I'm trying to move this downwards. Of course, the force is helping me go downward. As a matter of fact, if there was no friction, if the friction is zero, this load would go down the slope by itself. So it is usually the friction that hold it in place. And you all may recall the example, if I change the angle up to a certain point, the load would go down by itself without even having to have a lowering force. But we are going to use statics to calculate this PR, the force needed to raise my load F, and PL, the force needed to lower my load F. I would like to mention that the lead angle lambda has or is equal to L over pi dm, the inverse tan of L over pi dm, where L is the lead, the vertical distance that the screw would go through every time it goes through a complete rotation. So going through the perimeter, the average perimeter, using the median, the mean diameter between the major and the minor. So again, this is the applied force, and there is a nut here. And again, I'm looking at the raising force or the lowering force. So let's do some equilibrium and look at this free body diagram. So for raising the load, if I take the sum of the forces in the x direction, and from left to right is positive, I have a PR. Then I have the horizontal component of N, and it's going in the negative direction. So I will have a minus N sine lambda, and I have the horizontal component of this Fn, which I'm going to multiply by cosine lambda. So I'm going to have minus Fn cosine lambda is equal to 0. If I take the sum of the forces in the y direction, upward is positive, I will have a minus F, minus Fn sine lambda for the vertical component, plus N cosine lambda for the upward vertical component of this normal force. I have another free body diagram that I use for the lowering load. So if I do sum of the forces in the x direction here, I have the minus PL minus N sine lambda plus Fn cosine lambda. With the vertical component, sum of the forces on the y, F now is, I have this minus F again. I have a plus Fn sine lambda instead of a minus, and I have the plus N cosine lambda. So we have two equations for the raising load, and we have two equations for the lowering load. We can eliminate N and solve for raising load and lowering load. So I get here, if I use the first two equations, I get a PR, and the second two equations, equations B, we calculate PL. So I have an expression here for PR, and you see that I have F times sine lambda plus F cosine lambda, So this raising load is going to have to carry both the load and resist the friction. The lowering load, as a matter of fact, the force now is working with us and we just have to resist the friction. So the lowering load, of course, would be less than the raising load. If I divide the numerator and denominator by cosine lambda and use the relationship that tan lambda is equal to L over pi dm. So if you look here, this is pi dm and this is L. And this is the lead angle lambda. So I have here tan lambda is equal to L over pi dm. And this is the relationship we're going to use to simplify. I get the expression that PR would be equal to F times L over pi dm plus F divided by 1 minus FL over pi dm for the raising. And we have another expression here for the lowering force. Now, when I am trying to raise or lower this screw, I really cannot apply the force as a horizontal force as shown here. But I'm going to apply this rotation or a torque. And this torque, if you look at this PR, is really going in the horizontal direction, would be applied along this median diameter in a tangential direction. And this would be used to calculate the required torque to raise or lower the load. And if I just take the resultant of these tangential forces on the mid-range diameter, multiply it by the moment arm, I can find the torque. And in this case, the moment arc is equal to dm over 2. So in order to find the raising and lowering torque, I take these expressions that we found here and multiply it by dm over 2, which is what we're doing here. So we have dm over 2 and dm over 2 to find the torque. And these are these expressions simplified simply by multiplying dm over 2, and I'm simplifying them to get equations 8.1 and 8.2. So these are the torques that are needed to raise or lower the screws supporting a force F. When we look at the lowering condition, when I look at the lowering condition, so if this force, if I want to go down, really what's resisting here is the friction. And without exerting any lowering loads, the minimum friction that would just hold this in place, so when it's at the verge of going down, we refer to this as a self-locking condition. Self-locking condition. So when this lowering load is 0, and this is just kept in equilibrium, this is a self-locking condition. And we want to look at this. So if I look at my torque and consider that the lowering torque is negative, this would mean that the load will lower itself by causing the screw to spin without any external effort. And I don't know if any of you have experienced that. If you have like a nut that is on a screw, on a bolt, and this is very well lubricated, so the friction is very small and it's placed in a vertical direction. A nut may attempt to lower itself by itself without exerting any torque. If the lowering torque is positive, the screw is self-locking. When there is this torque that is needed, so this is self-locking. So what is the condition of self-locking? It is that condition similar to an object of an inclined surface where pi f dm is greater than lambda, this lead angle or the angle of inclination of the slope. And of course, we can easily prove that, as I mentioned here, if I go back to my equation and simply in this equation for PL, set that lowering force to be equal to 0. So it is at the verge of going down without applying any torque. You will be able to come to this conclusion, which is the same again as having an object on an inclined surface at the verge of failure. So this is the condition here. L over pi dm equal to 10 lambda. This is the tangent of the lead angle. But self-locking condition is when pi f dm is greater than lambda, or I would say equal to lambda, is at the verge of failure. The self-locking condition can be seen to only involve a coefficient of friction and the lead angle. So you see here in this self-locking condition, it involves the lead angle where it has L over pi dm. So if I change this here, I can write it as the friction is greater than L over pi dm, or the friction is greater than 10 lambda. F greater than 10 lambda. This is the locking condition. At the beginning of this discussion, I mentioned that when we are using the wedge or the lever idea of simple machine, that there is a mechanical advantage. But also we can calculate an efficiency by thinking about the output versus the input. And the efficiency is calculated by finding the ratio of the output to the input. So if I'm trying to raise a force, this efficiency may be calculated by using the output divided by the raising torque. So the output torque divided by the raising torque. The question would be, so what is really the output torque? So if I look at my free body diagram, my output is raising this load F. And if I'm just looking at the output, the torque that is needed without having any friction, the torque that is needed without having any friction would be PR if I look here at this TR, there is this friction component. So if I have the output is really resisting a friction which is not needed to lift the force F. So if I subset the friction to be equal to 0 in this equation, I would get an output of we can of course simplify that. I would get this term is going to be 0, this is going to be 0, so we get FDML divided by 2 pi dm. So I end up with FL divided by 2 pi, which is what you see here, FL divided by 2 pi. So this is my output divided by my input, and the input, so I have FL over 2 pi, and the input is this TR. So the efficiency of a power screw may be calculated using this equation 8.4. Now, everything that we've done so far is considering square threads. So how about if Acme threads are being used? This vertical F the load is applied in the vertical direction. But now if I have a thread angle of 2 alpha, remember with a square thread, alpha would be 0. Here now I have a thread angle that is equal to 2 alpha with Acme threads. Now the normal component is gonna become F over cosine alpha. So this force, if I look at the perpendicular to that surface, would be F over cosine alpha. So if Acme threads are used here, the thread angle creates a wedging action. So as a result of that, the friction components are increased. So the torque necessary to raise the load or tighten a screw is found by dividing the friction in equation 8.1 by cosine alpha. So I'm increasing the frictional component by dividing by cosine alpha as we're doing here. So I get equation 8.5 for the raising load should I be using Acme threads. On top of that, you may be using a collar on your screw to support the load F. So every time you are applying a torque and rotating the screw, not only are you resisting the friction between the threads, but there is an additional component of the torque to account for the friction between the collar and the load. So this is the collar in pink and the load in gray, and there is additional friction between them. So if you assume that the load is concentrated at the mean diameter, then this additional torque from the collar would be equal to the force multiplied by the friction between the two surfaces multiplied by the diameter of the collar or the mean diameter of the collar DC. Having understood the mechanism and the efficiency and the force, the torque that are needed to raise or lower a power screw, as in machine design, we would like to make sure that we design these power screws to handle the stresses that are going to be induced on them. So what are these stresses that we need to calculate? There is an axial stress in the screw of the body, in the screw body, and this is simply equal to the force divided by the area, the force divided by the area, and the area would be pi d r squared over 4. So I have here F divided by pi d squared over 4. There is also a shear stress from the torsion of the screw body, and I use the torsion equation. So I have tau is equal to T divided by J times rho, or like we did it in the shafts, we know now that's equal to 16T divided by pi d cubed because the screw has a circular cross section. Next, we look at the stresses in the threads. You see the forces applied on the threads are developing bearing stresses. They are bearing. There are two, there is another thread, there is the if this is the external thread, there is an internal thread that is carrying or supporting the load that is sitting on top of this external thread. And this is a bearing force that causes to a bearing stress. And the bearing stress is easily calculated by dividing the force over the area to which the force is applied. And this area may be calculated using the mean diameter of the DM for that screw. So I can use pi DM, the perimeter, multiply by the width here, which is P over 2, which is P over 2. As we have seen for threads, the height of a thread is P over 2. So this is what I'll be using to find the bearing area. So this is the bearing area, pi dm times P over 2. And then if you notice here, I have this nt, because the force is not going on one single thread, but nt would be the number I'm dividing by the number of engaged threads. So it depends if the load is distributed between a number of threads, that would be the number nt. So this is a bearing stress sigma b. Next, we also have bending stress at the root of the thread. So the root of the thread is right here. And if you think of the thread as a cantilever that is being fixed where it attached to the body of the screw, I have this force applied halfway towards the free end to this cantilever that is developing a bending moment. And this moment would be equal to the force multiplied by P divided by 4. So when I'm going to calculate the stress, I'm going to use the moment of F P over 4. As you see it here, F P over 4 is the moment. Now, to find the bending axial stress, I define the bending moment by Z, where Z is I over C. Z is sometimes referred to as the section modulus, where really the equation, the most common equation that you're familiar with is M over I times C. So here, you take this I over C and call it Z. So I is the moment of inertia of the section at the root of the thread. So if we look at it, I am looking at a width that's equal to the perimeter. So I have pi dr, and we have here nt, the number of threads being engaged, multiply by pi over 2 squared divided by 6. So P over 2. P over 2 is the height of the section. So we're looking at B h squared over 6. Now, you may recall that I for a rectangle section is BH cubed over 12, and then you multiply by H over 2. You divide by H over 2, and this is where we get this pi H squared over 6. So I go like pi over 24, here when you simplify this, times dr nt p squared. This is the moment, so I take the moment, I divide it by Z, and I get this equation 811, where sigma b is equal to 6f divided by pi dr nt times p. Now again, we can simply use the equation, but I would like you to understand about how we applying what we learned from solid mechanics and intro to machine design into calculating threads, into calculating stresses in the threads of power screws. We also have this shear stress at the center of the thread. And this is a possible shear failure mode involving stripping of the threads, either of the nut or of the screws. It depends on the relative strengths of nut and screw material, which one is going to strip first. And this is due to the transverse shear stress at the center of the root of the thread. And we can use the maximum shear stress equation from a rectangular section where tau in bending, tau is equal to 1.5 V over A. This is specific for a rectangular section. So we're dealing with the thread as a rectangular section, and the maximum shear stress will be at the center. So if I substitute for V, I use F. For the area, I'm using pi dr for the perimeter. The height is P over 2, and NT is the number of threads engaged. This can be simplified to 3f divided by pi dr nt over p. Put here everything together. So this is not a new stress, but if we consider a point where the stress is applied, and I'm going to consider the root. And if I consider this plane of the root as the xy plane, have an axial stress in the screw body of 4f divided by pi dr squared acting in the y direction. So I get here, this is 4f pi d squared r in this vertical direction. Now, this is, I'm referring here to the top of the root plane. So this is the root. I'm referring here to the top of the root plane. So I'm taking this in the y direction at this root. I'm also looking at the shear stress that is resulting at the top of the root plane would be coming from the torque, which is 16t divided by pi d cubed r, comes here in the yz direction. And in the x direction, I have the stress from the bending, the axial bending stress, which is 6f divided by pi dr nt over p. So that's coming here. So the tau xy is 0, and the stress, the axial stress in the z is 0, and tau zx is a 0. So really what we're looking at here at this point has a z component. So we're not looking at a case of a plane stress, but a 3D stress. And I can obtain the equivalent stress or the von Mises stress using equation 514 and use this and a failure criteria to find a design factor. I think everything that I covered here is very well explained in the example in the following slides that I'm going to leave you to read by yourself. And if you have any questions, I will be happy to take them. One last thing before I let you go, I would like to mention that thread deformation in a screw nut combination, usually the screw thread is in compression, causing elastic shortening of the screw thread pitch. The engaging nut is in tension, causing elastic lengthening of the nut thread pitch. Therefore, the engaged threads cannot share the load equally. Experimentally, like we use this NT, the number of threads engaged, we found that the first thread carries 38% of the load, the second 25, the third 18, the seventh thread is free of load. So clearly the first thread carries the majority of the load. Therefore, when we were looking at NT, in order to find the largest stress in the first thread, because that's the one that's exposed to the max, I can use NT to be equal to one thread, and instead of using F, I would use 38% of F in my equations. I ask you to please go over example 8.1, and this would help you to complete homework 12, which is due the end of the week.